An unexpected echo of space-time suggests a new theory of relativity. The discovery of gravitational waves was the crowning glory of Einstein's relativity. They might now have provided the first hint of something to scupper it. A long time ago in a galaxy far away, two black holes collided. We know this because more than a billion years later, on the morning of September 14, 2015, we felt it. In the world's most exquisitely sensitive measuring device, laser beams shifted ever so slightly as ripples in space-time washed over our Earth. This first detection of gravitational waves was the culmination of an epic scientific quest and a stunning endorsement of general relativity, Einstein's landmark theory of gravity. Since then, our detectors have seen them 5 more times, but this is just the start. And although everything we have learned from the first waves is consistent with Einstein's masterpiece, the coming deluge of sightings could tear it apart. Gravitational waves carry us into uncharted waters, where the fabric of the universe is so warped and gravity so extreme that our best theories are pushed to their limits. If there is something wrong with general relativity, we're going to find it here, says Salvatore Vitali at the Massachusetts Institute of Technology. As engineers recalibrate the lasers to make the detectors yet more sensitive, physicists are buzzing with anticipation about what they might reveal. Theorists are now entertaining cosmic oddities that could transform our understanding of black holes, gravity, and space-time itself. Their anomalous signals will not be easy to find. In some cases, we hardly know what we're looking for, but one group of physicists is claiming that we have already spotted them. Our modern understanding of gravity was sketched out in 1915 when Einstein put the finishing touches on his theory of general relativity. Its predecessor, set down by Isaac Newton, was a suitable approximation at small scales, but it broke down once you considered objects like stars and planets. In Einstein's new picture, gravity was a result of massive objects warped in the fabric of the universe to create depressions that would pull in anything nearby. Despite being tested again and again over the past century, its predictions have never been found wanting. The one idea we could not scrutinize was that massive bodies approaching each other would squeeze and stretch space-time so dramatically that they would spread ripples out in every direction like a pebble dropped in a pond. The trouble was that although the events thought to produce these gravitational waves were extremely powerful, the waves themselves would be incredibly gentle. Space-time is stiff. It does not vibrate easily. To stand a chance of seeing gravitational waves that have traveled billions of light years across the cosmos, you need to register wrinkles as small relative to us as we are to the Milky Way. That was the challenge of the scientists who dreamed up the Laser Interferometer Gravitational Wave Observatory, LIGO for short, in the late 1960s. Today it consists of 2 L-shaped detectors, one in Livingston, Louisiana, and the other in Hanford, Washington. Each uses mirrors to bounce synchronized laser beams up and down 4-kilometer-long arms. When a gravitational wave passes through, the arm lengths vary almost imperceptibly, and yet the beams shift measurably out of sync. But achieving this sensitivity was only half the battle. It also took a monumental effort to figure out what the signals coming out of LIGO should look like and how we could tease them apart from all the other vibrations passing through the detectors. Astonishingly, the 900-strong LIGO scientific collaboration pulled it off. They can now not only spot a gravitational wave from across the universe, but even decode the information these distortions carry. That's how we know the masses of the black holes producing these waves, for instance, or the collisions of ultra-dense neutron stars can seed the cosmos with heavy elements. Even so, the era of gravitational wave astronomy has barely begun. Since LIGO's second observing run ended in August 2017, the detectors have been receiving upgrades that will significantly improve their sensitivity. They have also been joined by a third detector, Virgo, near Pisa in Italy. The result is that when the third run starts, we should be picking up gravitational waves at least once a week, and the signals would be clearer than anything so far. And that will ramp up the chances of seeing something that does not fit with general relativity. This is not to denigrate Einstein, says Richard O'Shaughnessy at Rochester Institute of Technology in New York. He says, but there are good reasons to think his theory breaks down on some scales. The best known difficulties are two cosmological ingredients thrown in to bring general relativity's predictions into line with observations. Dark matter, which is unseen stuff dreamed up to explain why galaxies seem to rotate faster than their measured mass allows, and dark energy. So dark matter and dark energy. Dark energy is a mysterious influence pulling the universe apart at an even increasing rate. Then there is the fact that general relativity is incompatible with quantum mechanics, the theory of all the fundamental particles and forces, excluding gravity. For the most part, quantum theory reserves its predictions from the world of the very small, but when it comes to black holes, it has something important to say. According to Einstein's picture, the event horizon of a black hole represents a surface beyond which nothing can escape its pull. For all its importance as a physical border, the horizon itself is insustainable. That is, there is nothing there. But quantum mechanics suggests there should be a firewall, a ring of high-energy particles that would incinerate anything that passes. There was never any way to test the idea, but soon after LIGO's first detection in 2015, two independent teams proposed that a firewall, or indeed anything of substance at the event horizon, would reflect gravitational waves from colliding black holes. As long as there is something there, you should get echoes, says Nyayesh Afshordi at the Perimeter Institute in Waterloo, Canada, who leads one of the groups. He said, the question is, how long after the merger to expect them? In 2016, Ashfordy's team came up with a simple model for what could be at the horizon and figured out how far apart the resulting echoes would be. Then they looked at the publicly available LIGO data. What they found was jaw-dropping. For each of the three gravitational wave signals they checked, the black hole mergers were indeed followed by echoes and precisely the intervals predicted. Or were they? Ashfordy's calculation suggests that with no firewall, the chances of obtaining a similar signal from the random noise would be 1 in 100, falling significantly short of 1 in 3 million figure required to convince his peers. If Shorty's claim to check out, however, it would be the first direct contradiction of general relativity, and that would leave two options. Either Einstein's theory would need to be rewritten to accommodate the firewall, or we would have to abandon the notion of black holes altogether. In that case, general relativity could still survive more or less intact, so long as some pretender emerged to mimic the behavior of these cosmic beasts. See, when is a black hole not a black hole? Either way, it would be a big revolution, says Paolo Pani at Sapienza University of Rome. Naturally, not everyone is convinced. When members of the LIGO collaboration completed their own analysis earlier, the chances that random noise could have caused a similar signal doubled. The team also pointed out that the strongest evidence for echoes came from the black hole merger, with the lowest statistical significance. In other words, the loudest echoes came from the faintest signals, which is suspicious. Imagine someone was shouting at you and you hear no echo, but then you hear a whisper and get echoes from that, says Nicholas Eunice at Montana State University. Doesn't that seem a bit weird? For now, many cosmologists believe that Afshordy's claims are premature, but that could change as theorists get better at modeling the signals they expect firewalls to produce and as the data analysis improves. One thing is for sure, the hunt for black hole echoes is well and truly on. The LIGO collaboration has even made this one of its official goals. Now we have competition, says Afshordy. They are a huge force, so on the one hand, it is intimidating, but it's nice that this has been recognized as a worthwhile exercise. The gravitational waves washing in over the next couple of years should definitely settle the issue. Oh, it's beautiful, says Louis Lerner, also in the Perimeter Institute, who is not involved in the studies, saying when LIGO switches on again, we're going to have many more events. So if this thing is real, the signal we get stronger. If not, we move on. That's what's so nice about the scenario, adds Pani. That this is something that can be verified or ruled out in the next few years. Still, others refer to the chase less speculative prospects rather than seeking exotic phenomena with dramatic consequences for Einstein's theory. They're tweaking the underlying equations to see what they imply for LIGO observations. In some cases, these modifications could solve cosmological conundrums. In others, they might smooth the way to a viable quantum theory of gravity. Either way, says Eunice, with modified theories of gravity, you're building on solid foundations. You don't have to make up the shape of signals based on ill-defined ideas of what to look for. Instead, you add fresh ingredients to Einstein's equations and solve them to build a full prediction of what you expect to see in these extreme conditions, and then you test it against the data. The trick is to find weak spots in those foundations. General relativity has served several core principles, and from those arise specific predictions. That gravitational waves will travel at the speed of light, for instance, or that they preferentially corkscrew anticlockwise along their direction of travel. You break one of these principles and then you ask what would be the consequence, says Eunice. The LIGO detections so far have already killed off several modified theories of gravity that purported to explain dark matter or dark energy, including some that predicted space-time ripples would travel at below the speed of light, but there are plenty more where they came from. Eunice, for his part, is partial to the theory that conjures an extra field into existence. It couples to gravity in such a way that it would explain why matter was not annihilated by antimatter in the first moments of the universe, and thus why the universe is not filled with radiation alone. Such modifications imply that gravitational waves would be more likely to corkscrew clockwise rather than counterclockwise. That would in turn mean that we would observe black holes spiraling into one another much faster and more violently than relativity predicts. Emmanuel Berti at the University of Mississippi is among those exploring alternative theories of gravity. He says we all have our own favorites, but the broader point is that these theories are mathematically tractable. In other words, we know how black holes should behave if these theories are correct, so we can accurately predict how the gravitational waves it produced should look. In that regard, firewall echoes have some catching up to do, but with LIGO's upcoming campaign promising to so much equality data, even those who remain unconvinced are happy to admit that we can now entertain them with a straight face. The LIGO collaboration has been extremely conservative for good reasons, says Lerner, but now we know it can detect gravitational waves. The possibilities embolden riskier strategies, and this is just the beginning of the story, and it's going to be amazing, he said. And this is by Daniel Cosson's New Scientists, Unbended Reality. Please leave your comments, and thank you for your support. Kindly support my Patreon account. The daily posts are 5 videos daily, and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.